Hello! In this video, we are going to prove the following theorem. Let A be a set, and suppose R and S are equivalence relations on A. If A modulo R is equal to A modulo S, then R is equal to S. Okay, so before we get into the proof, I would like to mention a few things first. To start, if you recall, an equivalence relation is a relation that is reflexive, symmetric, and transitive. Right, so I've just abbreviated it, reflexive, symmetric, transitive. And second, if we have some element, say y in A, then the equivalence class of y with respect to R is the set of all elements M in A, such that M comma y is an element of R. And similarly, the equivalence class of y with respect to S is the set of all elements M in A, such that M comma y is an element of S. And another thing is A modulo R is the set of all equivalence classes with respect to R for elements in A. So to be an element of A modulo R, what that means is that you're an equivalence class with respect to R for some element in A. Similarly, A modulo S is the set of all equivalence classes with respect to S for some element in A. Okay, so now let's get into the proof. Let's suppose that we've already declared a set A, and let's suppose we already have two equivalence relations R and S already declared. Our goal now is to prove if this is true, then this is true. And to do that, suppose this is true. Our goal from here is to deduce that R is equal to S. And the way we can do that is we can show that everything in R is also in S, and everything in S is also in R. Let's start by showing that everything in R is also in S. To do that, give me an arbitrary element of R. I'll call it x comma y. And what we want to do now is we want to show that x comma y is also an element of S. Now, first, because x comma y is an element of R, clearly this means x and y are both elements of A. Right, so we have that x is an element of A and x comma y is an element of R. So x satisfies all the requirements to be an element of the equivalence class of y with respect to R. But wait a minute, the equivalence class of y with respect to R is an equivalence class with respect to R for some element in A, namely y. So the equivalence class of y with respect to R must be an element of A modulo R. And since A modulo R is equal to A modulo S, it follows that the equivalence class of y with respect to R is an element of A modulo S. So, the equivalence class of y with respect to R is an element of A modulo S. What does that mean? What that means is that the equivalence class of y with respect to R is an element of this set. So really, the equivalence class of y with respect to R is an equivalence class with respect to S for some element in A. I'll call it Z. Okay, but since x is an element of the equivalence class of y with respect to R, and the equivalence class of y with respect to R is equal to the equivalence class of Z with respect to S, this means that x is an element of the equivalence class of Z with respect to S. And what this means is that x comma Z is an element of S. So, we have shown that x comma Z is an element of S. But wait a minute, that's not what we want. We want to show that x comma y is an element of S. Okay, well then, how can we do that? Maybe Z is equal to y? Well, right away, I can't see anything that we have here that would allow us to use equality. So maybe it is not necessarily true that Z is equal to y. Okay, well, what if we could show that Z comma y is an element of S? Because if Z comma y is an element of S, then we would have x comma Z and Z comma y, both elements of S. As a result, we could use transitivity to say that x comma y is an element of S. and that's what we want. So let's try showing that z comma y is an element of S. Here's how we can do that. First, note that y comma y is an element of R. Why? Because R is an equivalence relation, so R is reflexive. And what this means is that y is an element of the equivalence class of y with respect to R. And since the equivalence class of y with respect to R is equal to the equivalence class of z with respect to S, it follows that y is an element of the equivalence class of z with respect to S. And what does this mean? It means that y comma z is an element of S. But since S is an equivalence relation, we know that S is symmetric. So since y comma z is an element of S, we can swap these around and say that z comma y is also an element of S. So now we have that x comma z and z comma y are both elements of S. Now we can use the fact that S is transitive to write that x comma y is an element of S. So we started with an arbitrary element of R, and we showed that same element must also be an S. Therefore, everything in R is also an S. So we've shown that everything in R is also an S. So now what we would like to do is we would like to show that everything in S is also in R. But you know what? I'm actually not going to show that everything in S is also in R. Because it turns out that to show that everything in S is also in R, what you can end up doing is exactly the same argument that we already did. It's just everywhere you see an R, you replace it with an S. Everywhere you see an S, you replace it with an R. And that's it. So a similar argument as above shows that S is a subset of R. Right? I'll leave these details up to you, but it's really the same thing that we did above. And yeah, these two facts together tell us that R is equal to S. And that's exactly what we wanted to prove, and so we are done. And so yeah, this is one way in which you could prove this theorem. And yeah, that's pretty much it for this video.